So the purpose of this lab is to demonstrate Newton's second law by observing the motion of an object that is moving in the same speed without changing direction. So the physics principles behind this lab are Newton's second law. Newton's second law states an object will stay at a constant velocity as long as the net force acting on the object is zero. So basically, an object in motion stays in motion. The main formula associated with this law is F net equals mass times acceleration. Also, F net divided by mass equals change in velocity over change in time. So in order to conduct this experiment, we need to make several assumptions. The velocity must be constant, so acceleration will be zero. The ball must travel in a straight line, and there will be no other forces acting on the ball, such as air resistance or friction. This ensures that F net equals zero. So here's my clip of the foam ball moving on track grip. You can see as the object moves, for each frame, I had to set the position of the ball so the movement can be tracked. And from this data, the tracker creates a graph and a chart. The graph is a position versus time graph, and the chart also shows like the X and Y at each time, the location at each time. So the ball will be moving in a horizontal surface on the X-axis to the right of my set origin. As the ball moves, there are forces acting upon it, such as the right-facing force of the original push of the ball, the downward force of gravity, and also the left-facing force of any friction that is acting on the ball from the carpet. As you can see in the position versus time graph, it looks like it has a pretty linear slope. There is a slight curve though. This linear slope suggests a constant velocity, but since there is a curve, we must compare it to our computational model to gain more insight. From tracker, there are several observations. First, the ball's initial position, and then the ball's initial velocity, which is at 1.537,800 meters per second. The initial velocity was derived from the average velocity formula, which is just simply change in position over change in time. And then also the duration of the clip, or the time of the last observation. So now we can take our observations and use them to create our computational model on GlowScript. This computational model will show my expected path for the experiment based on Newton's second law. Some things I had to add to the GlowScript code are the ball's mass, which is 0.02 kilograms, the ball's position and velocity, as I mentioned before, and more importantly, I had to edit the ball's velocity and the ball's position function to match the principles behind Newton's second law. So for the ball's velocity equals the initial velocity plus F net over ball's mass times delta t. So when you run the code, you can see that the trajectory of the expected path is straight and the slope is linear. This is expected because it shows a constant velocity. So in this model, there are no other forces acting upon the ball. So after creating the computational model, I loaded all the data points from the experimental model and data points from the computational model onto Google Sheets to create a graph. So looking at this graph, you can see that both of these lines start linearly. The red represents the computational model and the blue represents the experimental model. You can see that the experimental position diverges from the model position around 0.323 seconds, because the experimental model's velocity did not stay completely constant, though it should have. This is because the net force in the computer model was equal to zero, but we cannot control that in the real world. So in the experimental model, the velocity is decreasing because the ball is slowing down. Whereas in the computational model, it's a linear line, which means the velocity was constant. Though our experimental model did not support the expected results completely, it was still beneficial to show the two and understand why they differ. So there were several lab questions we had to answer. Question 1. What if we change the orientation of the axis or flip the axis? The ball would still travel in a straight line and it will still have the same speed. This is because the orientation does not affect this. However, the ball will move in a different direction because the orientation is different. And graphically, the slope would be different too due to the different orientation. And the position and velocity vectors would have to be adjusted for this. What does it mean when we set our net force equal to zero? This would mean that the forces in our system will negate each other, so the ball will travel in a constant velocity. So for example, like gravity and normal force will negate each other since they're acting in opposite directions.